This conference will now be recorded.
Very good evening, students. Today we have got few more questions from JEE Mains 2021 26th August paper shift 1, and today we have picked up questions from the 12th portion alone. Okay, so without much delay, let us start our discussions. We'll read the questions one by one and try to solve them. Let me change the ink to blue maybe. Yeah. So the first question says an inductor coil stores 64 joule of magnetic field energy, dissipates energy at the rate 640 watt when current of 8 ampere is passed through. If this coil is joined across an ideal battery, find the time constant of the circuit in seconds. Let us read the question once again. An inductor coil stores energy, that is very fine. So inductor coil having inductance L stores magnetic energy, and that can be written as half L I square. Okay, I square. I is the current passing through the circuit. Okay. Okay, so an inductor coil stores 64 joule of magnetic energy and dissipates energy at this much rate. Okay, the rate of 640 watt. That means, see, any inductor coil inherently will have certain resistance connected in series with that. So it is storing magnetic energy, at the same time it is dissipating energy as heat energy also. When a current of 8 ampere is passing through it, and if this is connected to an ideal battery in the sense we are taking DC battery, then find the time constant of the circuit. That means, you have got LR circuit, but you have not been given what is L, what is R, neither the voltage is given. You have been given the energy stored in the inductor coil and energy dissipated through resistor are given. So this is actually 64 joule. So from here we can find out what is this L. So let us find out. L is equal to, sorry, L is equal to, this is 64, that is fine. So you have got 8, so 128 divided by I square. I is what? I is this much. Okay, 8, so 8 square ampere square. So this will give you actually Henry. Okay, because we are having all terms in standard unit, standard SI unit. So this is, look, by this, that means, what you get 2 alone. Okay, let me cross check. So this will be, this I square is 64, this is actually 2, so I have got 2, right? So let L be 2 Henry. Okay, and R I have to find out. R, heat dissipated through R is given as I square R, which is again 640 joule per second. That is the watt. Okay. So what is R? R will be then 640 divided by I square means 8 square, that is 64. Then it is 10 ohm. Okay. So we have got L and R. Now you have to find out what is time constant. Time constant tau is given by L by R. So what is L? L is 2. What is R? R is 10. So what is the time constant? 0.2 second. Let us see the options. See the option B, sorry, option C will be the correct answer for this question. So this is really a very interesting problem, and you know these informations, but you might be in confusion how to find out what is the time constant. So in that case, you have to remember what is time constant. T is equal to L by R. That expression you have to remember, and then you have to know, actually intuitively understand that this energy which is dissipated through the coil is actually dissipated through the resistor. Okay, so that you have to understand. So these were two important important points to understand and keep in the mind while doing this problem. Okay, so let us go to the next problem. Again, there is a problem from LCR series circuit. Say, so the question says a series LCR circuit driven by 300 volt at a frequency of 50 Hz contains a resistance 3 kilo ohm, inductor an inductor of inductive reactances XL 250 pi. This is in ohm, but the capacitor is actually unknown. So in the LCR series circuit, this is an AC circuit obviously. So R is given as 3 kilo ohm, that means 3 into 10 to the power 3 ohm. C is unknown, and L is given as, see, L is not given, but what is given is XL, and frequency is given. This I can find out easily. Okay, let me find out what is L. See, XL means what? Omega into L, right? So from here, XL by omega. Okay, XL is given by 2 pi, sorry, it is given as 25 pi ohm, right? 25 pi ohm. So omega is again written as 2 pi. If frequency is given 50, okay, so this pi goes off, this and this I can write 5. So you know what you get, L is equal to 2.5 Henry. Okay, so we got that. If we require the value of the capacitance, see, you have to find out value of the capacitance to maximize the average power should be. So value of the capacitance, what should be the value of the capacitance, so that the average power will be maximized in the circuit. Oh, that is very great. Okay, so maximum power would be obtained in series LCR circuit only when it it is in resonance. That means XL must be equal to XC. Okay, XL must be equal to XC. So what is XL? XL is given, then you have to find out what is X. See what is C. XC means 1 over omega C, and XL is given 250 pi. Okay, all right. So what is C? I'll have to take reciprocal of this. So 2 pi F into C is equal to 1 over 250 pi. Okay, this is the one. So from here we have to get what is C. Let me do this calculation here. C is actually 1 over 2 pi into F into 250 pi. 1 over 2 pi into 250 pi, the frequency 50. Okay, and then yeah, so these are the things, 250 pi and 2 pi into F. So 2 pi into F into 250 pi. Okay, so if you do this calculation carefully, what you should get, see this pi square in the question, it is written that pi square can be taken as 10. Okay, so look then what I get. So 2, 250 and 50, here pi square means 10, right? So I'll get 50, see 100 here. Okay, so here it will be 100, 250, this is 100, so the another 2 and here another 1. Okay, so I'll get this much. Okay, this is in farad. So if you want to have microfarad, then you multiply 10 to the power 6 here. Okay, so divided by, there are 4, right? There are 4. So here look, I get 4. This is actually microfarad. Okay, because I have multiplied 10 to the power 6 here, so I'll get 4 microfarad. Okay, microfarad. Let us see the options over here. Yeah, option B is there, microfarad. So that will be the answer for this question. Okay, now let us go to the next problem. Okay, this is again a very interesting problem, but not very tough. This is also a very easy question. This is from photoelectric effect. In a photoelectric effect experiment, ultraviolet light of wavelength 250 nanometer is used with lithium cathode having work function phi is equal to 2.5 electron volt. If the wavelength of the incident light is switched to 400 nanometer, find out the change in the stopping potential. Okay, so to solve this problem, let us first find out or write down the equation, the famous photoelectric equation given by Einstein. So Kmax, that is the maximum kinetic energy with which photoelectrons come out, is equal to the incident energy. So that we can write AC by lambda, because these are given in terms of wavelength, AC by lambda minus phi, that is the energy of the like work function. Okay, this is the work function energy. Okay, work function. All right, so this is actually the photoelectric equation. Here we have to actually find out, the difference in the wavelength, difference in the stopping potential when the wavelength changes from 280 to 400 nanometer. So it is very simple. See here, stopping potential is actually written as EVS is equal to the Kmax. Okay, EVS is equal to K max. Okay, that means maximum kinetic energy is exactly equal to the stopping potential. Okay, stopping potential energy also I could say stopping potential energy. So E into Vs actually is stopping potential energy, EVS. So AC by lambda minus phi. So now look, I'm sorry, this is AC by lambda. This is AC by lambda. AC by lambda. Now these are all actually in the unit of energy. And what I can do, I can write this EVS1 for one wavelength, but the work function is not going to change because the photosensitive material is the lithium cathode for both the time. This is equal to Hc by lambda 2 minus phi. Okay, so this is the thing. Now look what we can do. We can actually uh, take the differences. Okay, difference. This say equation number 1 and this is equation number 2. I can just take differences. Look, then I'll take that. So E V is 1 minus E V V of S 2. Actually I should write in this way, EVS1 minus EVS2, that is, see, if I just subtract, so I'll get this one, this two will actually cancel each other, so this minus this, so I get AC by lambda 1 minus AC by lambda 2. So these are the thing. Okay, now what is this AC? I can take common, right? AC 1 over lambda 1 minus 1 over lambda 2. All right, so this AC I can write as 1240. I think this is in the unit of electron volt. Electron volt into nanometer, I hope. Hc by lambda. Yeah. So this is having energy unit. So energy into energy by wavelength. So Hc by lambda. Okay. All right. So this is actually the formula or the thing we have got. See this E I have to actually get this Vs1 Vs2, the difference between them I have to get, see, from here 1 over lambda in the nanometer. Oh, this has got actually unit of electron volt into nanometer. Okay, this AC has a value, this has got unit electron volt nanometer. Okay, that's how you get electron volt from both sides. Okay, so if we subtract them, nanometer anyway has gone, so I have electron volt both side. Okay, so I have this electron volt nanometer has gone, so I have 1 by 280 1 over 400. Okay, so we can actually do the LCM. 400, take 4, 70, 100, so 10, 7, 10. Okay, so you get this. So this is here 10 and this is 70, I guess. Is that 70? No, 7, just 7. Okay, so this will be actually 3 by 2800. So 2800. Okay, so from here, okay, so what we have got, look, this difference we have to find out where HC I have here multiplied with this. Okay, so 3 into this by this. Okay, so electron volt, the electron volts will actually cancel from both sides, here, here. So E into V, so there will be the dimension of voltage alone. Okay, so if you divide this 3 into 1240 into 3 divided by 2800 is actually that is going to give you 1.3 or something. Okay, so I think 1.3, yes, so nearly 1.33 from here. Okay, so we have got the answer 1.3. Here you look, we have got one option like that, so that is option A. So option A will be the correct answer for this question, and this will be actually in volt, because from both sides this will be electron volt into EV into nanometer, this quantity. So nanometer cancels out, E cancels out from both sides. Okay, so you will have ultimately volt. Okay, unit volt. All right, so guys, this was a very simple problem, but you have to do a little bit of calculation, that's all. Okay, we'll just move on to the next problem. Okay, now this problem is again very interesting. The problem says white light is passed through a double slit and interference is observed 1 point sorry, this, let me check. Yeah, so I think now it is clear. Yes, so earlier the right portion was blocked by this thing. Okay, so white light is passed through a double slit and interference is observed on the screen 1.5 meter away. The separation between slits 0.3 millimeter. The first violet and red fringe are formed 2.0 millimeter and 3.5 millimeter away from the central fringe. So if you have a double slit arrangement, so this screen distance is given, that is screen to source distance is given, slit distance, that is 1.5 meter, and suppose this is the central fringe position. So this is suppose small d, that has got 0.3 millimeter dimension, and you look here, uh, violet is seen here somewhere 2.0 millimeter away from the central fringe, and this is 3.5, okay, almost here, so 3.5 millimeter away. So these are the distance actually which we write as xn. Okay, so the question is the difference between the wavelengths of red and violet light is. So positions are given. This position is generally written as xn is equal to n into d lambda by small d. Okay, n into d lambda by small d. Here Since n is not mentioned, we'll take both of them as the first order. Okay, we'll take them as the first order. Okay, so x, so for violet and for red, so for red we'll write this x to be d lambda r by small d, and for violet we'll write d lambda violet by small d. Right, now look, we have been given this x, see x red and x violets are given. Now let us put those values. So x red is actually 0.2 is equal to, okay, let us, we have to find out the difference between the wavelengths. So let us find out the wavelength itself. So this is d lambda r by small d, and here it is 3.5 d lambda v by small d. Let me cross check whether, okay, violet is 2 and red is 3.5. So this is red, let me clean this. This is violet, this is red. Okay, so from here, look, these terms are actually common. These terms are common, right? I can take just ratio, isn't it? I can take ratios. So 2 by 3.5. Okay, here you'll get lambda v. Okay, lambda v, and you get here lambda r. Okay, so you have to take the difference actually. I think I have done a little bit wrong step over here. Okay, so this I get, fine. I have to take the difference. Okay, so I cannot move from here, I hope. Yeah, so better to just find out lambda v from here. So 2 into small d divided by capital D, and here lambda r I can get 3.5 into small d divided by capital D. So from here I can actually find, see, violet will be always having small wavelength. So I'll just keep this here like this. So d by d, this is anyway common. So you get 3.5 minus 2, that is 1.5 into small d by capital D. Capital D is given as 1.5. See this, this is millimeter, right? So let me just do one thing. I'll put the values now. So I'll get, so this is in millimeter 10 to the power minus 3. Okay, so D is again 0.3 millimeter. So that I'll put here 0.3 into 10 to the power minus 3 divided by D. D is given as 1.5 meters. So this cancels out. Then I get 3 into 10 to the power 3 into 10 to the power minus 7 as the difference. Let me see how the, okay, so I have to find out in nanometer. Okay, so I have to find out in nanometer. So 300, right? I have to multiply and divide both 10 to the power 9 meter. So nanometer, so 300 nanometer. Okay, so the difference between the wavelengths of red and violet will be 300 nanometer. So this is the answer for this question. Now let us move on to the next problem. This problem says, a particular hydrogen-like ion emits radiation of frequency this much when it makes a transition from n is equal to 3 to 1. The frequency in hertz of radiation emitted during the transition from 2 to 1 will be dash. So look, I can actually see this one. Let me write, or let me write in nu itself. Nu is, see, nu, H nu is actually the energy, right? So how do you get the energy? So energy we get Cz square into R. So this constant, let us take that as K. Okay. So all this constant I'll take as K, and see, I'll just directly write the expression for the frequency, which you also have to remember. Okay, let us write that F1 is equal to some constant K is equal to 1 over n final square minus 1 over n initial square. Okay, so this is the thing, this is the frequency. Okay, now I have got another one, K 1 over nf square minus 1 over ni square. You might be thinking why I'm writing the same thing for both f1 and f2. No, I'm just going to put the values here. See, nf for the first case 3 to 1, so 1 is the initial, sorry, final, and initial is 3, so 1 over 9. So what you get here is uh, 9 minus 1, so 8 by 9k. Okay, so for this case what you get, k into initial, so final is again 1, and here initial is 4, so what you get here is 3 by 4 k. Now let us take the uh, okay, I have to find out what is the frequency. So f2 by f1 is equal to f2 by f1 is equal to 3 by 4 k, and f1 is 9 by 8k. So this k goes off, and you know what you get, 27 by 32. Okay, and see, I have to find out what is f2. F2 is actually 2, sorry, 27 by 34 into the given value over here. So this is 2.92 into 10 to the power 15. Okay, so this is what is given. Now you have to find out the frequency. Okay, so frequency you have to find out in hertz. Okay, so if you solve this problem, like simplify this calculation, what you are going to get. So you just do this calculation, you will get nearly 2.46 into 10 to the power 15 hertz itself. Okay, 2.46. So here the problem was of this type, I think, or let me check whether there were options given. Yes, there were options given actually. Let me tell you what are the options. Options were 4.1 into, sorry, not that one. Options were 2.46 into 10 to the power 15. Then option B was 4.38 into 10 to the power 15. These are all in hertz. Option C says it is 6.57 into 10 to the power 15. And the last option says it is 0.44 into 10 to the power 16. Oh, sorry, this is 15 again. 15. So out of all this, so this first option will be the correct answer for this question. Okay, so we'll move on to the next problem again. So this is actually a very interesting problem, and probably this is a really unique type of problem from the capacitor, parallel plate capacitor. Let us try to understand the problem and try to solve it. Okay, so this problem says The material filled between plates of a parallel plate capacitor has resistivity 200 ohm meter. Generally, inside a parallel plate capacitor, the dielectric material we use is an insulator. An insulator. Insulator means what? It will have nearly like almost infinite resistivity or resistance, whatever you say, insulator. Okay, but here in this case, the material with which the space between the plates of the parallel plate capacitor is filled has actually low resistivity compared to the dielectric material. Okay, that means this will be conducting whenever there is a potential difference across it. Okay, whenever there is a potential difference across it. Now look this, the value of the capacitance is given 2 picofarad. The potential difference across the plates are given, that is 40 volt is applied across the plates of the capacitor. Then the value of the leakage current, what is the leakage current flowing out of the capacitor. So what is leakage current? If this material between the plates is a conducting one, then as you apply the potential difference, there will be flow of current through this. Okay, flow of current through this. Okay, it will be conducting, and that particular current is actually called leakage current. So what is this leakage current? We have to see, we have been, I think, given the options. Let me give you the options first. Let me give you the options for this problem. We have to find out the leakage current. Okay, so leakage current options are given as 0.9 microampere. Option B says it is 9 milliampere. Option C says it is 9.0 microampere, and option D says it is 0.9 milliampere. So what is leakage current? As I said, since this material is not a perfect dielectric, there will be current passing through the material. Okay, material itself. So that particular current is actually called leakage current, and that is written as I is equal to the potential difference V across the plates divided by R, that is the resistance of the material. And here see, the resistivity of the material is given. Let me just then go ahead with this. So leakage current I is equal to V by R, and see what I can write. This V I can write as electric field into D, right? So this is, see, electric field is actually sigma by K. K is the uh, relative permittivity of the dielectric material, or dielectric constant, you can say sigma by K epsilon naught into D. Okay, so this is actually V, and what is this R? R I can write as rho L. L is here D by A. A is the area of cross section. Now let us put this here. Okay, V I'll put sigma into D by K epsilon naught, and in place of this R I'll put here rho D, and A will be going in the numerator. This D cancels out, and this sigma into A I'll just write as the charge in the capacitor plates. Okay, let me write that as Q. So that will be Q by this. So this is at any arbitrary time actually. Okay, this expression is for any arbitrary time, and see this Q I can write as Q0 e to the power minus T by CR. Okay, here rho is K into epsilon naught. And see what is CR again? CR. See R, we have got this one. Okay, let me find out what is C. C we know K epsilon naught A by D, and write down this R. R is rho D by A. So this A cancels out. This D cancels out. So C into R is eventually going to become rho into K epsilon naught. Okay. So we'll just put it here. Q0 is the steady, like the maximum charge stored in the capacitor plates, and that charge is the steady state charge after the capacitor plates are fully charged. This is e to the power minus T by rho K epsilon naught divided by here rho K epsilon naught. Okay. Now we have to find out. See, the question was the leakage current. Okay, and see the relative permittivity is given. That means K is given as 50 here. See, this is the 50. Okay, so for the maximum value of the current, for maximum value of the current, the charge will attain the steady state value. Okay, so that particular situation will actually consider maximum value of the current, leakage current. Okay, so what will be the maximum value of the leakage current? So this exponential term will not be there in that case. Okay, steady state value. So Q0, I can write directly Q0 by this. Okay, so what I can write, the I is equal to I max. See, maximum will be uh, Q0 divided by Q0 means steady state charge stored in the capacitor divided by rho K epsilon naught. Okay, the time variation will not be there after a long time. Okay, or the steady state value. This I can write as C, the capacitance of the capacitor, and V is the potential difference across the plates of the capacitor. Okay, rho is given. Okay, K and epsilon naught. Okay, let me just put the values. C is actually given, I think, that is 2 microfarad, sorry, picofarad, that I can write as 2 into 10 to the power minus 12 farad. Then V is given as 40 volt. Okay, then K is given as 50. All right, and epsilon naught I can use at 8.85 into 10 to the power minus 12 farad per meter, I think. Yeah, okay, so this I can use. So if we put these values, so C is 40, sorry, 2 into 10 to the power minus 12, 2 into 10 to the power minus 12. C is sorry, V is 40 divided by rho. Rho was given 200 ohm meter. K is given 50. Epsilon naught 8.85 into 10 to the power minus 12. This 10 to the power minus 12, this minus 12 will cancel each other. And if you do further and further calculation, you will get C 903 microampere, and in milliampere it will be 0.9 milliampere. So this is the answer for this question. Let us just see here. Look, this first option will be the correct answer for this question. Okay, so I'll just stop it here for today. In the next class, we'll take up the next next set of questions from this set itself and try to finish the paper, this particular paper, as soon as possible. Okay, so guys, you have learned what is leakage current. That is new so far. we have not discussed about leakage current. So this you have to learn, and this is the take home message from this session. Okay, so thank you for your patience. Bye for today.